All right, welcome back, guys. In this video, we're gonna go over how to graph exponential functions and perhaps introduce a little bit regarding what the inverse function of exponential function look like in terms of the graphs itself. So let's get started. I'm just gonna briefly do several examples, kind of give you an idea what the graph looks like for exponential functions, maybe discuss a little bit domain and range as well. So let's start with the definition here. We define an exponential function f is given by f of x equal to a to the power of x, right? Where x is any real number and a is greater than 0. It will make sense if a was 0 because 0 to anything is going to be 0. We also restrict that a cannot equal to 1 because if a was 1, 1 to any power is going to be itself. So it won't be an interesting graph to really talk about at all. And we call the a is just the base. When you have exponent, the number that raised to any power, we call that number is a base. So it's going to be in the form of a to the x, where that's going to be the parent form, right? We can have some variation of that form later on, but that's what the parent graph or the general form of exponential look like is a to the x. And the input x, where we choose the value of x to plug in to get the y value, is going to be used as the power, right? So we have x is freely chosen, so I'm just picking the 6th number of x here for the sake of this example. And we choose a equal to 2 for the first example there, right? And f of x is just a y value, right? So this is just a y value right there, right? So let's start with 0. If x is 0 and if a is 2, then we have 2 to the 0, that's going to be 1, right? So that's our first y value there, 1. And then the order pair, the point that we can use to plot to create the graph is going to be 0, 1, right? So that's our first point, 0, 1 right there. Okay. Next, if x is 1, 2 to the first power is going to be 2, so a point is going to be 1, 2. So 1, 2 is going to be right there. X is 2, y is going to be 4, third point is going to be 2, 4, so 2, 4 right there. If x is 3, 2 to the third is going to be 8, so it's going to be 3, 8 for the next point. 3 is right there, 8 is right there. Going to the negative sides of x values, if x is -1, we have 2 to the -1. That is the same thing as 1 over 2 to the first, which is going to be 1/2. So we have -1, 1/2 as our next point. So -1, 1/2. Here's -1, right? 1/2 is going to be on the y-axis, so it's going to be half right there. So it's going to be right there, right? If x is -2, 2 to -2 is going to be 1/4. So -2 and 1/4. Here's -2, 1/4 is about right there, right? Very close to 0. And then 2 to -3 is going to be 1/8. So 1/8, and then -3, 1/8, just very close. It's getting very, very close. So those are just the 6 points we picked there. So of course, this is not the only 6 points. So there's are infinite many points on this graph. We call them solutions. So our goal is to plot some points, getting some insight to the general behavior of the graph for the exponential function that is, and then kind of sketch it, the general behavior based on the points that we plotted. So I think at this point it's safe to assume that the graph would just follow these points here. It's going to have a curve like this here. Kind of careful, right? Now the question is, will this graph here ever touch 0? I know based on what I sketched, it looks like it touches 0 or touches the x-axis there, but the question, will it ever touches 0 on the x-axis? The answer is going to be no, because let's say suppose x is -10, for example. If that's the case, the y value is going to be 2 to -10. That's going to be 1 over 2 to the 10th power, and that's still not going to be 0. That's going to be very, very, very small, closer to 0, but it is not 0. So it's important that when we draw this graph, we know that the graph or the y values never touches 0, right? So from this graph here, we can start, extracting the domain and range. So the domain, as remember, is a set of all inputs or the x values that we use for this function, which has, an y value that I get mapped to, right? So based on the graph here, based on this here, or just the way the function defined, we are freely able to choose any x values, as you can see there, whether it's negative infinity to positive infinity, we can choose anything, and therefore the domain is negative infinity to positive infinity. Okay, x can be any values because we pick anything for x, we guarantee to get y that comes out of that, right? And then the range, which is the graph itself, the range is the y value, which is the graph, right? That graph there is always above the x-axis. So if you look at the y-axis, come from the y-axis, this is 0. So the domain is always going to be just from here to positive infinity. But remember, it can't be equal to 0 because no matter what value of x we pick, the y value is always going to be greater than 0. So therefore, our range is going to be from 0 to positive infinity, but 0 can't be included in the domain, or excuse me, in the range because there's no x that map to that, so we can use open parenthesis. As you recall from the previous video, we discussed one-to-one function. This is an example of one-to-one function. Why? Because one, we can use the horizontal line test, right? Any horizontal line test here will cross the graph one time, right? So that's going to be one-to-one function. Or we start out by picking two different x values. Let's say arbitrary. Let's pick this one and then pick that one, right? Notice that these two x values are different and they get mapped to two different y value, as you can see there. So it is a one-to-one. So it is. So exponential is a 1-to-1 function. Okay. So we got the domain, we got the range, we got the graph. Let's see what else, any other features about the graph at all. We'll come back to it if there's something comes up. So now we're gonna look at another example that's very similar to this, but our base, the number a here, our base is not 1/2, but it's the reciprocal of that is gonna be, it's not 2, but it is reciprocal, which is going to be 1/2. So that's our base here. A is 1/2 right here, right? So we're going to graph this function here, and then we're going to compare this to that and see if there's any similar or difference, that give us insight how to graph future exponential functions. So let's get to that. When x is 0, we have 1/2 to the 0 power. Anything to 0 power is going to be 1. So we still have this point 0, 1. So 0, 1 is right there, right? When x is 1, we have 1/2 to the 1 power, so that's 1/2. So 1, 1/2. So 1, 1/2 is right there. When x is 2, we have 1/2 to the second power. So that's 1/2 times 1/2, that becomes 1/4. So we have 2, 1/4. So 2, 1/4 is right there. And then when x is 3, we have 1/3 to the third power. So that's 1/2 to the third power. So that's 1/8. So 3, 1/8. 3 is right there. 1/8 is very close to that. Going to the negative side of x. When x is -1, 1/2 to -1. Now, if you remember your exponent definition, this is when you have a negative exponent, you're gonna have 1 over that number, but in this case 1 over that number is 1/2, so that just becomes the reciprocal 1/2. In this case, I'm at 2, so we have -1 and 2. There it is. When x is -2, 1/2 to -2, that's gonna be 4, so -2 and 4 right there. And -3 for exponent is going to be 8. 3 and 8. -3 and 8 is up here. So there it is. That's our graph. Let's go ahead and connect this and and see what it looks like and compare that to the previous graph there. All right. So if we using the reciprocal base, the graph itself is just kind of reflecting, kind of flip-flop across the y-axis, as you can see there, right? And the domain, looks like the domain is still the same. The range is still going to be the same, right? The only thing different is the graph is going to flop itself across the y-axis, right? So if we're using the same base but reciprocal, then the graph is just going to reflect across the y-axis. Let's look at some of the translation here. Okay. So we'll see if we can match these graphs here. We got 3 examples, and we want to see which graph matched with which functions here. So 2 to the power of x plus 1, negative 2 to the x, 2 to the x minus 1. So let's see, if you remember from chapter 8, graph translation, when you graph a function and if there's a variation within the parent graph. So in this case here, right, you have 2 to x as the parent graph, and then this is just add 1. So what does that mean? And here's a negative in the front, and then here's this subtract 1 here. So one way you can do it to match this is plug in the points, right? Let's say, this one has 0, comma 0. So let's plug when x is 0, for this one, we're going to get 2. Well, that's wrong. So, it has to be this one here, right? So when x is 0, we're going to get 2 for this one. So that gotta be a right there. So that's one way to kind of match these function to his graph. Another way is to understand the graph translation, and we're not going to go into too much about it, but as you recall from chapter 8, by shift it horizontally or vertically, or flip it across the x-axis, those are the 3 things there. You have a negative here, for example, you have a negative in front of the 2 there. So that's going to be making all the y values negative. So if all the y values negative, you're looking at this graph here, right? For example, when x is 0, negative 2 to the 0 is going to be negative 1. And that's going to be this point there. So that's another thing you can tell, just pick these up as you go, is how do I know, just shortcut or just pretty quick what the graph look like based on the translation. Over here, so this is B, right? Part C here, this function C. Notice that, you subtracted 1 after you take 2 raised to the x. So every single y value after you raise it 2 to that x value is subtracted by 1. So you kind of like move all the y values down by 1. Now notice that earlier, these 2 graphs here, looks like this is the common point that the graph must cross, 0, 1. So if you move that down by 1, you're looking at a shift downward by 1 there, right? So that's something you pick up as you go, as you do more of this. So this is part C. So we can make this note here. So this right here is a shift down by 1 unit, and this here is a reflect across x-axis, and then this right here is a shift to the left by 1 unit, right? I'm gonna let you work on this example on your own here. What would happen if we have x equal to 2 to the y? So instead of y equal to 2 to the x, which is the graph that we have here, right? So that's y equal to 2 to the x. How will this graph change if we interchange x and y right there? I use the word interchange, as you remember from the last session, last video, we discussed inverse function. So one of the steps to find inverse formula is interchange x and y. So I'll let you guys work on this on and figure out what the graph looks like. But I'm gonna go ahead and start by just doing 1 or 2 points for you guys here. So now the y become the input, the x now become the output. So you want to choose y first. So for example, I'm gonna choose y equals 0, and that means x itself is gonna be 2 to the 0 is gonna be 1. But when you plot these points, you want to write the order pair as x comma y, not y comma x. So it should be 1 comma 0 for this first order pair there, right? X first and then y. So 1 comma 0 is going to be right there, 1 comma 0, right? I'll pick another point here. When x is 1, excuse me, when y is 1, 2 to the 1 is going to be 2. So we're looking at the order pair 2 comma 1 right there. And I'm going to let you figure this out. Can we pick a y that is negative? I think we can pick a y that's negative. Okay, I'll let you do -1 there too. So go ahead and fill all this up here, you know, as many points as you can, and you know, kind of sketch the graph on your own and see what will you get, and also discuss the domain range as well, and how that relates to the original graph. Essentially, this here is going to be the inverse of, you know, the y equal to 2 to the x there, and that's what you want to be able to get to when you finish this example here. And in the next video, next lesson, we're going to give this type of, there's a particular name for inverse function of exponential function, and we're going to introduce that in the next lesson.